In this class, we started by discussing systems of equations, turned those into vector equations, which then became matrix equations. Suddenly we're discussing linear transformations, a topic that seems radically different, but it's not. Linear transformations are a natural extension of what we've been doing. If T takes Rn to Rm is a linear transformation, then there is an m by n matrix, careful with the order, A, so that T of x equals A times x. In other words, you can think of a linear transformation as a matrix. You can also think of a matrix as a linear transformation, which you'll prove later. You probably have a few questions. How do I find the matrix A? How is that matrix useful? What am I having for dinner tonight? Let's take these a step at a time. In general, given a linear transformation T, the columns of the matrix A are given by T of each coordinate vector in order. Consider the transformation T takes R3 to R2, given by T of x1, x2, x3 equals x1 plus x2 and x3 minus 2x1. Our first step is to check if this is linear. We need to show those two things, and you should have these committed to memory. If you don't, pause the video and look it up. In fact, pause the video regardless and show that this is linear. Welcome back. Here's my proof that this is linear. Now that we know this is linear, we can compute A. A will have three columns since the domain is R3. The first column is T of 1, 0, 0. The second is T of 0, 1, 0. And the third is T of 0, 0, 1. Compute each of these. So the matrix A is 1, 1, 0 minus 2, 0, 1. Let's use this to compute the image of 1, 2, 1 in two ways. First with T, then with the matrix. They should come out to agree. First, T of 1, 2, 1 equals 3 minus 1. Next, we need to multiply the matrix A by the vector. Now, we don't technically know how to do this yet, but basically it's each row of the matrix combined with the vector. If this is confusing and weird, that kind of makes sense. We haven't done it yet. Watch this again in a week. It'll all make perfect sense, hopefully. The result is, again, 3 minus 1. So they agree. What is this good for? So many things. So many. We're going to need two definitions. First, a function is onto or surjective if every element in the range is hit by an element from the domain. As a picture, every element on the right has an arrow pointing at it. Everything gets hit. Second, a function is one-to-one or injective if every element in the range is hit at most once. As a picture, each dot on the right has at most a single arrow pointing at it. If you've taken discrete, you'll know that showing a function is one-to-one or onto can be tricky. But that's not true for linear transformations. A linear transformation T takes Rn to Rm is onto if and only if all the columns of A span Rm. A linear transformation is one-to-one if and only if all the columns of A are linearly independent. In other words, once you find the matrix A, put it into row echelon form. If every row is a pivot row, then the columns span Rm, so T is onto. If every column is a pivot column, then the columns are linearly independent and T is one-to-one. And this is so cool! I'm going to make an entire video discussing kinda how this works and how everything we've done so far ties together nicely. Let's return to our previous example and see if it is either one-to-one or onto. We already have the matrix A. There are two pivots, therefore it is not one-to-one. 2 is less than 3. But it is onto. 2 rows, 2 pivots. Finally, what are you having for dinner tonight?
I don't know. Tacos?
We're having tacos?
No. I was talking to the camera.
Tacos!
No.